All right, so now we're going to take a look at using these fundamental identities. So again, we're going to be taking large multiple function expressions and making them smaller, more compact, and containing fewer trig functions. Some of the strategies that we're going to use are some of the strategies that we were using the first time around, which is when in doubt of how to approach a problem, change all the trig terms into sines and cosines, look to use things like reciprocals, quotients, Pythagorean identities to substitute them in. If you have fractions, common denominators, algebraic manipulations such as factoring, GCF, foiling, distributing, getting a common denominator. If a strategy or substitution doesn't seem to help, go back and try again. And also never give up. Okay, so for example number 1 here, we're going to be taking a look at, we need to simplify secant of x minus 1 times secant of x plus 1. So I'm going to take a look at this, and my first thought is, I know there's a Pythagorean identity that has secant squared with tangents. So what I'm going to do is I'm going to take a look at that identity, which is, that identity is squared. So I'm going to want to try to get this so that this is squared. So foiling this is going to be our best bet. So foil, so distributing. So secant times secant is secant squared. Secant times 1 is secant. Negative 1 times secant is negative secant. And then negative 1 times 1 is negative 1. Combine your like terms. So these two are going to cross out. And then we have secant squared minus 1. Secant squared minus 1 is equal to tangent squared of x. And that would be the most simplified version of this. So we're done. That is the final answer. Okay, moving on. Taking a look at example number 2. Example number 2, we have some different things from what we're used to because we have cosine at a negative angle. Cosine at a negative angle right here, that is going to use our odd-even identity. So our odd-even identity tells us if I look at cosine of a negative angle, that's just equal to normal regular cosine, which, good, that helps us simplify. Because another thing that we want to keep in mind is whenever we're trying to simplify, we don't want to have negative angles. Negative angles is not something that we want to keep in our problems. All right, so let's bring along the rest of the problem. And then my thought would be, I've got multiple terms on the inside here. Maybe distributing might somehow help. So distribute in the cosine, distribute in the cosine. So now we have cosine secant minus cosine squared. Cosine and secant, those are reciprocals of each other. So that should, cosine times secant, that just becomes 1. So now we have 1 minus cosine squared. 1 minus cosine squared is sine squared. So that is as simple as possible. So again, odd even, distribute, reciprocals, and then Pythagorean identities. You'll notice that I'm not writing off to the side what steps we're using. That's because we're not verifying. We're just simplifying. Okay, so example number 3, we have sines, we have cosines, and we have that cotangent. So if I'm looking at that cotangent, I notice that that's not the same as the sines and the cosines. So I'm inclined to change that cotangent to being cosine over sine. So I'm looking to change that guy. Okay, so at this point, I'm kind of stuck because I've changed everything into cosines and sines. I have multiple terms. Generally, when we have multiple terms, we want to try to condense this down so that it is a singular term, so we need to somehow be able to add these together. To add these together, we do need to get a common denominator. So we're going to get a common denominator by multiplying the left-hand side by sine over sine. So now we have sine squared of t plus, and the cosine multiply together, so that ends up being cosine squared of t all over sine of t, your common denominator. Now, taking a look at what we have here, with this sine squared and this cosine squared, that's a Pythagorean identity. So that becomes 1. And then the sine just comes along. We have 1 over sine, which is cosecant. And that is our most simplest version possible. All right, so taking a look at example number 4, we're asked to simplify this whole thing. I don't like this written as divided by cosine squared, so I'm going to write this whole thing over cosine squared. Okay, taking a look at what we have here, I'm automatically seeing something that we haven't dealt with yet, which is this sine of 90 minus x. If we take a look back here with your odd-even identities, we do have this odd-even identity, that's sine of pi over 2 minus x equals cosine. As we had previously said, if you do have a pi over 2, it's replaceable for the 90. So in our example, we have a 90 instead of a pi over 2. So we can replace this for the co-function. So we have 1 minus the cosine, that just comes along. Then we have 1 plus, and then this sine 90 minus x, that just becomes cosine using the co-function identity all over cosine squared. I would say at this point that we should probably FOIL the numerator out. So 1 times 1, 1 times cosine, negative cosine times 1, negative cosine times cosine. This is going to give us 1 minus cosine squared all over cosine of x. Sorry, cosine squared of x. 1 minus cosine, that becomes sine squared of x over cosine squared of x. And then we can simplify this down into tangent squared of x. So that is our final answer. So again, it's a lot of substituting, replacing, and then doing some algebra skills. Okay, so taking a look at example number 5, we have this little note off to the side that is telling us that, so we're trying to simplify this. Note that breaking up fractions isn't hard to do. In fact, when you can, doing so is one of the easiest and most productive ways to solve identities. The trick is to break them up correctly. You can break up a fraction that has several terms in the numerator only. So notice how in this problem we have multiple terms in the numerator and we only have a singular term in the denominator. Okay, but you can't do it the other way around. If you've got multiple terms in the denominator, you can't break it apart. So by breaking this apart, we have now secant of x over secant of x minus cosine of x over secant of x. Now, taking a look at this, that is the same thing over itself. So that's just going to be 1. And then we've got this cosine over secant thing. So I don't like having the secant on the denominator. So if we move that up to the numerator, that becomes a cosine. So now we have cosine squared, and that's being subtracted from 1. And that just becomes sine squared of x. And that's our final answer. Okay, moving on to example number 6, which will be the last one of this particular video, just so that it's not too long. So we're looking at cosine plus 1 over sine plus 1 plus sine over cosine. I mean, looking at this problem, this is very irritating because it's the same thing except they're flipped fractions. There's not a whole lot we can really do about that. So what we can do is we can get it so that we have a common denominator. So 1 plus sine plus 1 plus sine over cosine. Okay, so we're going to do that whole thing where we multiply the other fraction by what the current fraction is missing. So this denominator does not have a cosine. So we're going to multiply in cosine over cosine. The other side is missing 1 plus sine over 1 plus sine. So distributing out our numerator, we now have cosine squared of theta plus 1 plus 2 sine of theta plus sine squared of theta. You want to make sure that with this one, when you are distributing, when you do the 1 and the 1, the 1 and the sine and the 1, and the sine and the sine, you have a 1 times sine and a 1 plus sine. So that's going to give you 2 sines. All right. And then all over cosine times 1 plus sine. I know this looks like a lot, and to some extent it obviously is, but if we take a look here, we have a cosine squared and a sine squared. We know that cosine squared and sine squared have a relationship. We know that these become 1. Ooh, and I'm really running out of room. Okay, so this becomes 1 plus the 1 plus the 2 sine all over, and I'm not distributing the numerator yet, not distributing the denominator yet, just because I don't quite know what's going to happen with that. Okay, so we have 1 plus 1 plus 2 sine over cosine times 1 plus sine. So we're now going to add in the numerator. So 2 plus 2 sine of theta all over cosine times 1 plus sine of theta. So I notice here that we have a 2 plus 2 sine and we have a 1 plus 1 sine. So we have something that's scaled up by 2 with something that's the original. So if we look at these two and divide them, they will divide down and they will actually cross out and just become 2. So we are left with 2 over cosine. So the very last part about this that we would want to do is we would want to write our final answer as to secant. And that is your final answer.